Okay, I think we finished up the blue handout last time. I think we did. Okay, two new handouts. Chemistry. The green is an outline, and we'll be working with both of these. I put together this new diagram. I'm going to think about putting this on T-shirts and coffee mugs, etc., and then offering them for sale. But this is largely the overview of some of the chemistry we'll be doing. Nucleophilic acyl substitution. Another NAS, but this is acyl substitution. Okay, leaving group on a carbonyl, often called an acyl group. Okay. Of course, there's many particulars and details here. This is a very general overview. Of course, we'll also be doing chemistry of nitriles, which do not have a carbonyl. Okay. So one thing that's very important here is converting between different carbonyl, different acid derivatives. Carboxylic acid is sort of the king. We can convert to every other acid derivative from the carboxylic acid. Some directly and some only indirectly. For example, we can convert a carboxylic acid to an acid chloride. You remember this was on the functional group list in Organic 1, either called an acid chloride or an acyl chloride. I usually say acid chloride, and many people do. We can also convert acid to anhydride. That's a new functional group. One functional group there. Anhydride. Or ester. This shows the interconversion. For example, anhydrides can be converted directly to esters or to amides. Esters can be converted to amides. All right. Eventually, what you should do with this diagram here is put reagents on each arrow. That's your objective here. All right. To help summarize and things. The things in the box, the middle derivatives, are shown in increasing order of increasing reactivity towards nucleophilic addition, which is the first step of nucleophilic acyl substitution. Okay, they're shown in order reactive. Thus, this is more reactive towards NAS. Again, a different NAS, more reactive than amides. But acid chlorides are more reactive than anhydrides towards acyl substitution. Okay? So this is my sort of diagram to help sort of illustrate some things. Everything in the box can be converted back to what? Carboxylic acid. Back to the base functional group, the king, or queen. We can do that two ways, either with aqueous acid. Okay, this takes you that way. How else can we do it? Well, leaving the box below, aqueous base. But if we do it with aqueous base, how is the carboxylic acid going to exist? That's right, in the basic form. It would exist as an anion. How do we put the proton back on to get to the neutral carboxylic acid? Acid. Right? Everything is here. Beautifully well-crafted diagram, you say?
Yes.
Thank you. And by the way, this is your least reactive species towards ACL substitution. Because it's an anion, it ain't going to react to nucleophiles that well. Nucleophiles are going to be like, whoa, I ain't going there. Anion alert. I don't like anions. I like cations or electron poor species. Okay, what can we do? Well, both, basically they go hand in hand. The green, number one, let's look at synthesis of carboxylic acids. Okay, 1A is a review of previous methods. Have we ever synthesized carboxylic acids?
Yes.
Yes. Here we go. We actually have done it several ways. Review. One is benzoylic oxidation. Everybody remember? Haven't forgot that yet, have you?
No.
Don't forget your review, right? Everybody agree with that? That's a way to make a carboxylic acid. So what's in your toolbox?
What do you think?
You know that commercial on TV? What's in your toolbox? Right? That's what, these are the reactions in your toolbox. All right, what's another way to make carboxylic acids? Oxidation of primary alcohols, yeah. Primary alcohol. What will do this? What will do that? One of the big three. What's actually the intermediate in going to here?
Aldehyde.
Aldehyde. But with water, you're going to get a diol. The diol will be oxidized. You get the carboxylic acid. Review. Any other ways to make carboxylic acids that we've seen? Yeah, well, if you just had an aldehyde, could you oxidize it? Yeah, we did it up there, but you could start with aldehydes. Remember the Tollens reagent? That's a reagent that's specific for oxidation of aldehydes. Silver ion. Okay. Ammonium hydroxide is used. It helps solubilize the silver. Makes an ammonia-silver complex to get things dissolved. That's the purpose of the ammonia. Ammonium hydroxide is just ammonia in water. Otherwise, it's a gas and it's hard to work with. Yeah? Of course, the big three will also do this. The silver ion is just specific. Any other ways we can make carboxylic acids? How about from alkenes? Oxidative cleavage of alkenes with like KMNO4. Remember? You're going to cleave this. Each carbon becomes carbonyl. Now, these are not carboxylic acids, but they're aldehydes. And what happens to aldehydes with like KMNO4? They're oxidized, so the ultimate fate is carboxylic acid when you have an H here. Okay? We could do this in a ring. And we give this, well, here you got a methyl, so that's a ketone, right? Ketones are not susceptible to further oxidation in this class. Aldehydes are. So the aldehyde gets oxidized to the acid. What's here? Ozonolysis? What would that give? We did this with ozonolysis. What's the difference? Aldehydes survive ozonolysis as long as you don't work it up with an oxidant, which can be done. And then you say, I thought ozonolysis did not give carboxylic acid. I thought, well, that's because you worked it up with an oxidant. I've always shown you working it up with a reducing agent. And aldehydes survive. Okay? Looked like good review. Were you aware of all those ways we make carboxylic acids?
Well, not PCC. Like PCC.
PCC? It doesn't give a carboxylic acid. What is that reaction used for?
Aldehyde.
Alcohol, primary alcohol to an aldehyde would stop. Very, yeah, how do you stop at the aldehyde? PCC is one thing that would do that. Or PDC, or Tollens reagent is a variety. PCC, pyridium chlorochromate. Okay, so there you go. What did we just do? A, review previous methods. Any new methods? Yes. B, a very nice new method for us is reaction with the Grignard reagent with CO2. Of course, we take an alkyl or aryl halide, magnesium, we're going to make Grignard reagent, right? And that's essentially the carbanion, right? It reacts as if it's that. Yeah? CO2. Lewis structure. Yeah? Lone pairs on oxygen. Okay. The carbon is electrophilic. There's a good amount of partial plus on this carbon due to dipoles. Now it's a net nonpolar molecule, but you got to understand the definition of polarity. Polarity is a response. This molecule will not respond to an electric field because it's not going to experience any torque, and so you have to have physics, but that's what polarity is. It's nonpolar. The carbon does have partial positive, and these electrons will add here, and either side you want to go move electrons this way, because oxygen is right here going, I want these electrons. And the chemistry flows this way, and now you get your electrons. What does this give? Well, that gives that. We just made that bond. And the electrons moved on to this oxygen to become the third lone pair. Does everybody agree that that addition of the Grignard to CO2 gives that, which is called what? What's the name for that type of species? It's not the carboxylic acid, it's the carboxylate anion, yes. Nomenclature video, yeah. How can we put the H on? Your favorite strong acid, okay? It's a neat, very neat way to make a carboxylic acid. CO2, is that a gas? Or what? What is CO2, physical form?
Usually a gas.
Usually. Explain.
I mean, CO2 is known like it can be in like solution. It can be. It depends on like what environment it's in.
CO2 can be solid, dry ice. Okay. Typically dry ice. What's easier to add, a gas or a solid dry ice? Much easier. Okay. So usually, instead of pumping in a gas, you just get some dry ice and put in. And by the way, you can just put in a whole bunch because when it warms up, it's going to evaporate out and be gone. It's not going to be an impurity. Very easy to get rid of CO2. It just evaporates out. Very nice reaction, okay? Note we are adding a carbon. This is 3 carbons, right? This is 3. That's 1 carbon. This is the number of carbons. And that equals what? Somebody? Danielle's awake. Taking her vitamins. Thank you. 4. Did I get that right? 3 plus 1 is 4? Okay. Another way to make a carboxylic acid. Use of cyanide as a carboxyl synthon. What is a synthon? Sort of like precursor. It's a precursor in your synthesis. That's kind of what synthon means. Here we go. Take an alkyl halide, right, with sodium cyanide, SN2, right? We can displace the bromine with the cyanide. But the cyano group is a carboxylic acid derivative. And as we shown in the very nicely designed diagram earlier, every carboxylic acid in the box can be converted back to what? Carboxylic acid. How? Either with aqueous acid or straight down was hydroxide. That's aqueous base. Okay? Yes. And so we can convert this with aqueous acid or aqueous base, either one, and we can get the carboxylic acid. This is 3, and that right there is 1, and that equals what?
4.
4. Now this is also 4 because the carbon of the cyano group becomes the carbon of the carboxylic acid. We'll be doing this later. Right now I'm not going to do mechanism. We will do this later. Mechanism later. It's just a hydrolysis though. What's the difference in formula of, well, it's more than hydrolysis because we've lost a nitrogen. It is a hydrolysis, but that's overly generic term. But yes, we reacted it with water and we lysed or cleaved something. Okay, note that both of these reactions begin with the same type of substrate in this case. So 2 different routes from the same type of starting material. Which reaction is best? Which pathway is best? Well, show a synthesis of this using those 2 methods. And then let's ask which method is best. Okay? Synthesis using both methods and then which is best. Do that on your own. We'll talk about that on Monday. Reactions of carboxylic acids. Basically, we've talked about thus far how to make carboxylic acids. Several review methods, okay? 2 new methods. All right? What's in your toolbox? Isn't that the commercial?
What is that a commercial for? Oh, what's in your wallet?
Oh, what's
Yes.
in your wallet? That's right. Okay. Now, what's in your toolbox? All right? These are the reactions in your toolbox. Okay. Reactions to carboxylic acids. Well, this is going to take more than 20 minutes like we spent on making them. Lots, because acid derivatives. All right? The first, and at this point we are doing the diagram. And the first we're going to be looking at, we'll be looking at each of these arrows. The first is converting carboxylic acids to acid chlorides. Okay? So it's all sort of here. Like chlorine, because acid chlorides are by far most common. They're reactive intermediates. They're used for a purpose. The chloride works great, so really, why make the bromide or iodide? Everybody just makes the chloride. It's most common, cheapest. We don't have to worry about iodine being a better leaving group, because since the leaving group leaves in the fast step, chlorine is fine. Acyl fluoride would actually be more reactive. Problem is, acid chloride is already so reactive, it's almost unstable. The acid chloride is even more unstable. So the acid chloride has just got the practical, that's it. And you just don't need any other halogens. Again, they're not going to be final products. Typically used as reactive intermediates. But how do you make them from carboxylic acids? Yes, it's an acid derivative. You gotta know what an acid derivative is. Nomenclature video. Okay, most common ways to react carboxylic acid with. We've seen that before. Name of that? Thionyl-chloride. We reacted alcohols to make alkyl chlorides. Very analogous. We replaced OH with Cl. We're doing that here. OH being replaced with Cl. We're going to make that over there. SO2. We're going to do mechanism. In general, does everybody agree that we have an acyl group here, which is general for a carbonyl group? We have something on the acyl group that is gone, so this must be a leaving group somehow. Maybe it had to be activated first. Cl minus must have been a nucleophile at some point, yes. Because electrophile ain't going to do this. So nucleophile acyl substitution, okay? Okay? The leaving group, something's going to replace the leaving group. All right? Most all these reactions are fall under that general chemistry or type of reaction. Here we go, thionyl chloride structure. Got the S. There is a lone pair there, complete Lewis structure. There's lone pairs on the other atoms as well. Whenever you do mechanism, you need full structure of everything. By the way, some pretty good job on the synthesis on the test. Okay. And there were actually probably for like the first one there was probably about 3 or at least 3 different ways that it could have been done, and you guys came up with all 3 ways. I mean, a lot of variety there. Multiple answers possible. Need some work on the spec. Okay. First step here. What do you propose? The sulfur of thionyl chloride is very electrophilic. It's got a lot of
OH. We're going to activate the OH so we can leave.
Uh-huh.
The oxygen is going to attack the sulfur.
Which oxygen?
The oxygen on the
Yeah,
carboxylic acid.
Well, the acid has 2 oxygens. Which oxygen are you?
Oh, I'm sorry. The OH.
Okay. I would say this is going to be the reacting oxygen. Add to the sulfur, and what are we going to do here?
It's going to kick back that double bond.
Pi bond. The weaker bond is broken first. The weaker bond is moved away from the sulfur. We've done this before, yeah? And that gives what? I'm just going to call this R. Maybe that'll save some ink. Oxygen now bonded to sulfur. Electrons up onto oxygen. That becomes a minus, yeah? And there's 2 chlorines. And there's an OH. 1 lone pair here, and a positive charge here. We'll continue over here. Why this oxygen? Which oxygen is more nucleophilic? The one I used. Why? Why is that one more nucleophilic?
Resonance.
Resonance. This oxygen actually has some partial positive charge. Everybody see that? Because if we could just do resonance here, these electrons here, resonance structure. These electrons here, electrons up. One of these lone pairs is conjugated. These are not conjugated. Because one of these is conjugated, we can draw this resonance structure. Partial positive. The true structure is a blend. The true structure of the carboxylic acid has some partial positive on this oxygen. All right? There's partial positive here due to 3 dipoles with polarity there. Which oxygen is more likely to be attracted to the positive sulfur? In fact, we can also say this. One of the oxygens up there has some minus character. Which one is it?
be them.
Which one has minus character? This one. Does it make sense that the one with minus character is going to be the one to be attracted and bond to the positive sulfur? Yes. That's why I'm reacting to the other oxygen. Okay. But never fear, because eventually we're going to get to the same thing you would think you were going to get the other way. It will come in just a little bit. For example, let's go ahead and get there. Because we can make this carbonyl. At this point, we can do resonance. And you can do these steps, and as we go forward, sometimes you can do steps in different order. Because we've got two sort of places where we can do resonance. These electrons here, these here. It's resonance here, yeah. R, O bond O, H. And this becomes O. Does everybody agree that's resonance? And that's part of the structure. And you see how we're back to, now the carbonyl is between this C and the O. And the oxygen with the sulfur now is sort of like single bonded, which is the same we might have gotten to if we had just bonded the single bond oxygen here. So we get there the same way, but it's better. It's a better mechanism because it accounts for reactivity of the oxygens. Okay. What can we do over here, Alex?
Oxygen kicks back.
These electrons back down. What's a better leaving group, Cl or neutral chlorine or neutral oxygen? Yeah, it'd be chlorine, more electronegative. And that gives what? We reform the double bond O, one chlorine left, plus Cl minus. What you want to do now? We're trying to get home. Let's make all three products. What do you want to do now?
Have chlorine attack the carbon that's bonded to the O and that's bonded to S.
We could, again, we can do steps, different steps here. We got sort of multiple things going on here. How about this? What if I go ahead and make one of our products? That can take this H, leave that behind. What does that give?
HCl.
Is this right? Two lone pairs plus HCl. I actually do not want to do that now that I look at it, because we don't have another Cl. Because what would I do next? Now I want to do what you said, but I don't have the Cl. I used it. I recognize that now. So I don't want to do that. Could. I need a Cl to do this, though. And it actually makes more sense because it's protonated carbonyl. Carbonyl with a proton on it, positive charge. We'll be doing that lots going forward. That's for your notes right there. It's a protonated carbonyl that occurred in our mechanism. Instead, let's have this act as a nucleophile. Okay? All right, you can draw it over here. Let's have it add here. What do we want to get? Don't we want to get a chlorine on this carbon?
Yeah.
We got it, okay. We do that, what are we going to do here?
Kick off the single bond oxygen.
Well, the pipelines.
Or the pipeline goes into oxygen.
Again, I have different ink, you do not, so I'm not gonna even try to use it. Don't confuse these arrows here. The only thing we're doing here is that here. When we add something here, what bond we're gonna break? Pi bond. This oxygen really wants the electrons because it's protonated. What does that give? R, OH, Cl down to that carbon, but we also have the O. Yeah? That's a nucleophilic addition. Again, you already have it. I'm going to erase it to make it a little cleaner up here so you can see it. Okay. Now at this point, there's no charge here. This ain't going to be isolated. Because anytime you can make a pi bond and kick off a leaving group, that's easy to do. This can come back. Which leaving group are going to kick off?
The O, S,
It could be almost either. But if we kick off the chlorine, what are we doing?
we're just going back to our.
You're going backwards. And many steps we do in mechanisms are often in equilibrium. They're often reversible. But if you go backwards, you ain't going forwards. How do we go forwards?
Kick off the.
We need to kick off this. And what does that give? Gives that, yeah? Plus what?
O.
Plus that leaving group. Is that a reasonable leaving group? Well, the answer is, this is fast. Because I've said it, you got to understand what I'm saying. Anytime you can make a pi bond and kick off a leaving group, that is easy and fast. And if it's easy and fast, we don't have to worry about leaving groupability that much. But we can still ask, is that a reasonable leaving group? Or does it have any stability?
It will if it forms SO2.
It's resonance stabilized. Now, this is going to actually do something. Because anytime you can make a pi bond and kick off a leaving group, that's easy to do. What does that movement give?
So two.
That's SO2. Plus what?
Chloride ion.
Cl minus. We got this. How do we finish up?
You form HCl.
What can take the H?
Chloride.
Yes, see how things fall together here? This takes the H, that leaves behind. What do you get? You just made all that. Multiple steps here, multiple decisions, doing things in different order. This is going to be our life with carbonyl chemistry. Okay? You don't just memorize mechanisms, and I know many of you have not been. You understand, you're able to work, do what needs to be done. Key steps that we sort of see what's going on. Protonated carbonyl occurred in our mechanism. Questions here?
When the OS OCl leaves, can you from the carbon, can you make those last two steps all in one where it just falls and kicks off the chlorine and forms SO2, or do we have to show it where in two separate steps?
A little bit up for debate. For me, I'd rather you always show things stepwise,
Okay.
because to me it will keep you out of trouble. Unless we know it's concerted.
Okay.
Then you have to show it concerted because we know it's concerted. If we don't, then I would recommend stepwise as much as possible.
Yes, sir.
Okay. Again, what we just did is we're going to see recurring in lots of our mechanisms. So that's the first look at sort of this. Lots of details there to be focusing in on. And again, not just memorizing each individual step, but it's just sort of the overall approach, process, etc. Very common reaction. The two products are both gases, unless there's water around. This tends to be a very nice, clean reaction. These two just can be evaporated out. All right. They're both acidic. SO2 is a Lewis acid, right? I'm sorry, it's an Arrhenius acid, which probably is also a Lewis acid. Definition of Arrhenius acid? Okay. Conversion to esters. We can convert a carboxylic acid to an ester directly. All right. This is done with an alcohol and an H plus catalyst. Strong acid typically when we say H plus catalyst. Now we have an R group here. Importantly, if we star this oxygen here, it's now that oxygen. That is, this oxygen is from the carboxylic acid. All right? That is, we are not just replacing this with an R. It's more than that. We're also, you might say we're also replacing the oxygen, but actually the water oxygen could be from either one of these. So I can't just star one of them. Because at one point during the mechanism, these two oxygens will become equivalent. And ultimately, then you lose water, it can be either one. All right, this is a example of this would be to take benzoic acid, ethanol, with a acid catalyst. We'll talk about this, and we can get the ethyl ester. Ethyl ester. Mechanism here. Okay. First example of this, although we referred to it before. When you're doing carbonyl chemistry and you have acid conditions, acid catalyst, the first thing you want to do is protonate your carbonyl. Okay? Protonate the carbonyl. Now ultimately, we can say, well, this is the leaving group, right? That's where we have to be careful. Lg. We're replacing this OH with OR. But again, I can't just do that because maybe it's the other oxygen that actually leaves. But very general, we could say, hey, that's the leaving group. How do you make this a better leaving group? Protonate. But we're not going to protonate the OH here because which oxygens more inevitably fill it? We referred to previous discussion. We showed resonance structure. Carbonyl oxygen. We're going to protonate the carbonyl oxygen with the strong acid, and we'll do that many times. A protonated carbonyl, like we saw in our previous mechanism. What what this does is it makes the carbon here more electrophilic. Look right here, there's partial plus here because of dipole. But there's more partial plus here. Why? You could say resonance. Which oxygen is going to pull more on the carbon, a neutral oxygen or a positive oxygen? Positive oxygen. The oxygen's like, hold on, I don't want to be plus carbon. You're going to have to give me some electrons. Come on now. It's going to pull even more. Protonation of the carbonyl makes the carbonyl carbon more electrophilic. We can even show resonance. I'll do that one time. Going forward, we will not. We can just actually move these up. If we move these up, we can get that here, resonance structure. And this shows us that that carbon has lots of partial plus character. I'm going to redraw this to just clean it up here. Lots of partial plus character here. Many ways to consider it. The alcohol then attacks here. And we move these electrons there. You can always work with any resonance structure. We could have done resonance first, and then add the ethanol just right there. This also gives the same thing. What does all that either way give? Okay, we need to draw this out. Ethyl, and there's an H here. One lone pair left. Okay? Ethanol can add to either resonance structure, just a protonated carbonyl form, or you can do resonance and then have your nucleophile add to this. Am I right? Is that nucleophilic addition? Right? That is a nucleophilic addition. And by the way, we did nucleophilic addition in the previous mechanism, I just didn't label it. Okay, at this point, remember I told you the oxygens have become equivalent? Look, they're equivalent now. They're both existing as OHs. All right, what do we need to do here? We need to kick off one of these oxygens and have this one there instead. But right here, this is the better leaving group. Let's do proton transfer. And let's finish this mechanism up here. That's going to move this H to one of these oxygens. Which oxygen do you want to move it to?
Other one.
It does not matter. I'm going to move it to the top one. That gives that. Got to know what a proton transfer is and why is there two lone pairs here? Well, that's because we only moved the H+. The bonding pair remained there as a lone pair. Okay, at this point, now, anytime we can make a pi bond, let's see, which oxygen? It doesn't matter. We can still get there. I'm going to do it with this one. Pi bond, kick off that oxygen because here, which is a better leaving group? Positive oxygen or neutral?
Positive.
Positive. What does this give? That gives that. Plus what? Water. Water. This is our product. What do we need to do to get home? There was a catalyst. right? There's got to be a minus here, maybe HSO4 minus, all right? Or maybe ACL. ACL could even be used here. I'll just do that so I can have just a smaller anion here. ACL could be used. And so Cl minus would take the H, and we get our product plus HCl reformed, acid reformed. Okay, we're pushing time, guys. I'm sorry. The important thing to say here is that every step here is reversible. Every step is reversible. Please look at this. That is, if you had the ester, could we protonate the carbonyl?
Yes.
If we had a protonated carbonyl, could water add to the carbonyl to give back this? Yes. If we had this, could this proton be transferred to this oxygen? Yes. If we had this, could one of these oxygens kick off this positive? Yes. If we had this, could we deprotonate and go back to here? Yes. Every step is reversible. Which side is the equilibrium going to lie towards?
Right.
This is an example of a truly equilibrium reaction. Most of our reactions are not, we haven't had to worry about equilibrium. This we need to, because every step is reversible. Think about that, and we'll pick up there on Monday.